NVIDIA Isaac Groot is a platform of sim-ready data, simulation frameworks, and synthetic data generation blueprints, and pre-trained models. NVIDIA Isaac Groot N1 is an open generalist foundation model for humanoid robots. Groot N1 features a dual system architecture for thinking fast and slow, inspired by principles of human cognitive processing. The slow thinking system lets the robot perceive and reason about its environment and instructions, and plan the right actions to take. The fast thinking system translates the plan into precise and continuous robot actions. While internet-scale training data provides common sense and reasoning, it doesn't teach robots specific actions or control. So we need better data, and more of it. Human demonstration data is limited by the number of hours in a day. With Groot blueprints for synthetic data generation built on NVIDIA Omniverse and Cosmos, we can exponentially multiply a small number of real-world data captures into a massive, diverse training dataset. Groot N1's generalization lets robots manipulate common objects with ease and execute multi-step sequences collaboratively. Across many environments, and even multiple embodiments. And with synthetic data generation and reinforcement learning, humanoid robot developers can post-train Groot N1 for their specific robot and task. The age of generalist robots is here, driven by developers building on NVIDIA Isaac Groot. NVIDIA is accelerating AI development for AVs with Omniverse and Cosmos. Cosmos prediction and reasoning capabilities support AI-first AV systems that are end-to-end trainable with new methods of development. Model distillation, closed-loop training, and synthetic data generation. First, model distillation. Adapted as a policy model, Cosmos's driving knowledge transfers from a slower, intelligent teacher to a smaller, faster student inferenced in the car. The teacher's policy model demonstrates the optimal trajectory, followed by the student model learning through iterations, until it performs at nearly the same level as the teacher. The distillation process bootstraps a policy model, but complex scenarios require further tuning. Closed-loop training enables fine-tuning of policy models. Log data is turned into 3D scenes for driving closed-loop in physics-based simulation using Omniverse neural reconstruction. Variations of these scenes are created to test the model's trajectory generation capabilities. Cosmos Behavior Evaluator can then score the generated driving behavior to measure model performance. Newly generated scenarios and their evaluation create a large dataset for closed-loop training, helping AVs navigate complex scenarios more robustly. Last, 3D synthetic data generation enhances AVs' adaptability to diverse environments. From log data, Omniverse builds detailed 4D driving environments by fusing maps and images, and generates a digital twin of the real world, including segmentation, to guide Cosmos by classifying each pixel. Cosmos then scales the training data by generating accurate and diverse scenarios, closing the sim-to-real gap. Omniverse and Cosmos enable AVs to learn, adapt, and drive intelligently, advancing safer mobility. To the creators, the pioneers, the builders of the future, Cuda was made for you. Since 2006, 6 million developers in over 200 countries have used CUDA and transformed computing. With over 900 CUDA-X libraries and AI models, you're accelerating science, reshaping industries, and giving machines the power to see, learn, and reason. Now, NVIDIA Blackwell is 50,000 times faster than the first CUDA GPU. These orders of magnitude gains in speed and scale are closing the gap between simulation and real-time digital twins. For you, this is still just the beginning. We can't wait to see what you do next. The world is racing to build state-of-the-art, large-scale AI factories. Bringing up an AI gigafactory is an extraordinary feat of engineering, requiring tens of thousands of workers from suppliers, architects, contractors, and engineers to build, ship, and assemble nearly 5 billion components and over 200,000 miles of fiber, nearly the distance from the Earth to the Moon. The NVIDIA Omniverse blueprint for AI factory digital twins enables us to design and optimize these AI factories long before physical construction starts. Here, NVIDIA engineers use the blueprint to plan a 1 gigawatt AI factory, integrating 3D and layout data of the latest NVIDIA DGX SuperPods and advanced power and cooling systems from Vertiv and Schneider Electric, and optimized topology from NVIDIA Air, a framework for simulating network logic, layout, and protocols. This work is traditionally done in silos. The Omniverse blueprint lets our engineering teams work in parallel and collaboratively, letting us explore various configurations to maximizing TCO and power usage effectiveness. NVIDIA uses Cadence Reality Digital Twin, accelerated by CUDA and Omniverse libraries, to simulate air and liquid cooling systems. And Schneider Electric with ETAP, an application to simulate power block efficiency and reliability. Real-time simulation lets us iterate and run large-scale what-if scenarios in seconds versus hours. We use the digital twin to communicate instructions to the large body of teams and suppliers, reducing execution errors and accelerating time to bring up. And when planning for retrofits or upgrades, we can easily test and simulate cost and downtime, ensuring a future-proof AI factory.
So as a large computing company, you might expect that NVIDIA would be interested in quantum computing. But in fact, the association goes much deeper than that. It's really in NVIDIA's DNA to care about quantum computing because we have a long history of enabling computing revolutions. NVIDIA is not trying to build quantum hardware. We're not trying to build qubits. We're not trying to build a quantum processor, but we are trying to build a device that will turn those qubits into a useful quantum computer. And we call that device an accelerated quantum supercomputer.
Cuda is based in Boston, and we make quantum computers using neutral atoms. Starting at the very low level, quantum computing requires error correction, requires measurement, and then very fast decisions on what to do with the measurement. These decisions can be done by classical hardware like GPUs.
An accelerated quantum supercomputer is a device that integrates quantum hardware with AI supercomputing. And you need AI supercomputing to solve the big scaling challenges that quantum computing faces. Challenges like error correction, control, and calibration.
The second area that quantum and classical meet is in the area of simulation. Before people run software on a quantum computer, they often like to simulate it to make sure that it works.
Simulation has always been a critical tool for developing computer hardware. NVIDIA GPUs undergo tens of thousands of simulations during their design, and it's a tool that will be just as, if not more important, in designing better quantum hardware.
So really, classical computers are instrumental or vital in all stages of the quantum development, all the way from the hardware up to software development and running the algorithms.
Quantinuum is basically a company which does quantum hardware as well as quantum software and algorithms. One key part of quantum computing is developing software. And you can see, people always talk about 1,000,000 qubits. Writing software for 1,000,000 qubits is not easy.
Software is just as important as hardware, and that's why we've built Cuda Q. Cuda Q is our software platform that allows users to seamlessly both access and control large-scale accelerated quantum supercomputers.
Where NVIDIA is really useful is they also provide libraries, okay, which run on GPUs. So in the software development flow, as long as we need to develop software for quantum computers, you will have to have the NVIDIA technology there to develop those scaled qubits, and then you scale it to a larger number of qubits. Right? So we use it extensively in our development internally. I've seen what GPUs have been able to do in the last 25 years. And I think the next stage of adding quantum to this is going to bring all kinds of new advances to science and to people.
It's become clear that to be useful, qubits need to be brought inside accelerated quantum supercomputers. That's why at NVIDIA, we're building them.